and welcome to our physics class. I'm your teacher, Mr. Juguna. We are going to do a Form 3 topic, proceeding from what is topic in our previous lesson. And for today, we are going to do the displacement time graph. This is a Form 3 topic, so I would urge any Form 3 student or Form 4 students or any other interested person to actually send an SMS to 21450 to confirm that in class. Please pick a book, a pen. We do this topic together, and to confirm that we're in class, you are with us, please send a text message to 21450. Thank you. We're still looking at the motion graphs, and we are now going to proceed with the displacement time graph. Remember, we say the first ones. For a stationary body, we write here displacement. Here it is in meters per second, is 0. We said for the displacement time graph, we must show it on both sides of the axis, because displacement being a vector quantity, it can be negative or positive depending on the position of the observer. So we must show it that way and then that way. That is now A for a stationary body. The second one, we can have, here we have displacement in meters. Sorry, not in meters per second, it's in meters. This is time in seconds. Suppose it's a straight line like that. This is a motion graph of a body moving with uniform speed. It's not speed, but velocity. Because we see from here, what we have on the y-axis, we have the change of displacement, and on the x-axis, we have the change in time. And from this, we can see the change in displacement of a change in time, that gives us velocity. We know from mathematics that the gradient of a straight line like this one is uniform. So because the gradient is giving us the velocity, then you can say here that the velocity is uniform. So this is a displacement time graph of a body moving with a uniform velocity. Not speed, but velocity. If it was distance here, you can say uniform speed. But because displacement, it is uniform speed. The rate of change of displacement with time is uniform. The other one, number 3, maybe it can be like this. We have the displacement, then here we have time, and then it is like that. So again, for the displacement time graph, the gradient, that's the steepness of any line or the curve, would give us the velocity. Now looking at this, if we can divide this into several portions, that's A, B, let me try to do it that way now. That way, then we have C there. Part A is almost flat, becoming steep, and even part C now becoming even steeper. So what does this steepness represent in this graph? It represents the velocity. So you can see here, because the steepness is varying, then we can say that the velocity of this body is also changing. So this is a displacement time graph of a body moving with varying velocity. Varying velocity. But we can see it is increasing. It is increasing. That the gradient at point at the region A is less steep than at B. As it becomes even more steep, that means the velocity is increasing as time progresses. So this being a curve, we can see the gradient there. We can do a point, the gradient at any given point. Because this being a curve, we have to ask ourselves then, how do you get the gradient at a given point? Maybe let me show it clearly. At this point, we drew a gradient at that point, then get the gradient of that line, which is actually different. That the gradient at different points is different. Because as for a line you have said, for a straight line you have said that the gradient is uniform. You can pick any point, even here or wherever. The gradient is uniform. But for this, for a curve, the gradient keeps changing. It keeps changing with time. And the gradient is giving us the velocity. Therefore, this is a body moving with a varying velocity. But as I've said, it is increasing. Now, if you look at this one here now, this is the displacement. This is in meters. Then here we have time in seconds, and then it's going like this. If you look at this one here now, again, the displacement time graph, the gradients gives us the velocity in meters per second. So again, if you divide now these figures in these various portions, maybe A, B, and C, and try to look at the steepness of all these places, you can see that C is almost flat. So when it's flat now, what does it mean? That the gradient is almost tending to zero. That means the velocity is decreasing. Here it's actually very steep, becoming less steep, and here is almost flat now, because the gradient is nothing but the steepness of a line or a curve. So here, at that point here, if we have to draw a tangent, we have the gradient at this point P. We have another point here, we draw a point there, we get the gradient, and then here, I don't know how you can even draw this. It's almost a flat line. So, but what I'm saying, that at point P and Q, the gradient at P is higher than at Q. That means the velocity here is actually decreasing. And here is almost now flat. And because the gradient of a flat line, of a horizontal line, is zero, that means the velocity is almost dying. So this is a curve. This is the displacement graph of a body that is moving with a varying velocity, but it's actually decreasing with the time. So that's the displacement type graph. So we have said, so far we have looked at the distance time graph, that we say the gradient gives us the speed. We have looked at the speed time graph. We have looked at the displacement time graph, where we have said that for the gradient for these ones, it always gives you now the velocity, which can be constant or it can be varying. The last category that we're going to look at is the velocity time graph. The velocity time graph is our fourth category now. So we have velocity time graph. So as I've said, velocity is on the y-axis and time is on the x-axis. So here we have the velocity. It must always be shown on the y-axis in meters per second. And remember, velocity we said is a vector quantity. Then here we have time, which is given in seconds. Now, again, we can have the first curve, which is a straight line like that one's. Being a straight line, it shows that the rate of change of velocity with time is uniform. That at, suppose this is 0, I have maybe here 2, this is maybe 20 meters per second, this I have 4 seconds, this corresponds to, let's say 40 meters per second. Then I have another one here, maybe 6, this corresponds to 60 meters per second. You can see as the rate of change of time is how velocity is changing, the time is uniform. From 0 to 20, you have 2 seconds. From 20 to 40, again, the gap there is 20, is 2 seconds. So it's uniform. So we can see here, we can say this is the rate of change of velocity here is uniform. And then I need to say here, the gradient or the steepness of a line or a curve on the velocity time graph, what does it give? It gives what we call the acceleration. It gives accelerations. I've said for the displacement time graph, it gives the velocity. Because here, let me remove these ones. I remain with my line. So I have that one there. If I need to draw the gradient for this line, I draw at least, I look for 2 Fredberry points on the y-axis and the x-axis. I'm getting the change in v. The y-axis is giving me the change in velocity. This could be v1, v2. So that is the change in v. Then on the x-axis is giving me the change in time. change in time. This delta means change in something, change. So I have now, I'm dividing the change in v, change in velocity, over the change in time. And from our previous discussions, we said that the change of velocity divided by the change in time is what we call the accelerations. So we can see now from this that the gradient of the first time graph, it always would give us the accelerations of that body. So we look at these ones. For us, when it's a straight line like this, is a body that is moving with uniform acceleration. Uniform accelerations. The acceleration of that body is uniform. The velocity is changing uniformly. Now, the other one that we can have is number 2. Is still is velocity, meters per seconds. Here we have time, and then it's moving like that. So we can see here, as I've said, this is a body moving with uniform, change of velocity is uniform, therefore uniform accelerations. And here we have a body moving with velocity changing non-uniformly. The velocity of the body is changing non-uniformly, and therefore the acceleration is different. Because the gradient is giving us here, we have said that for these ones, for the first time graph, the gradient gives us the accelerations. And therefore, because here the velocity is changing non-uniformly, it therefore would mean, therefore that it therefore would mean that the acceleration is non-uniform, that the acceleration of the body at this point is different from region P, Q, and R, because the gradient is giving us the accelerations. So the acceleration here is different from here and different from here. Here the body is increasing, therefore the rate of change of velocity in time is very high, therefore the body is seriously accelerating. Here it is picking up, because the gradient at all these points is different. Here it's very high, non-uniform, but actually it's increasing. Here it is not so high, but here the body is almost picking up. So as I've said, this is a body, velocity is changing non-uniform. It's a curve. When you see a curve, see it is non-uniformity as opposed to a straight line. The gradient is uniform. Therefore, for this one is actually uniform accelerations. But this one's, the curve is going upward. Therefore, the velocity is changing non-uniformly. Therefore, they have different rates of accelerations. Or it can be like this. Or also, this one is non-uniform. That one's here. This is velocity, and then you have meters per second. Here we have time. Also, this one is non-uniform, but with this one we see that it is decreasing. Therefore, at this point here, almost becoming flat at these regions. Here, the rate of change of velocity, when it's flat like this, the change of velocity over the change in time is almost tending to 0. And therefore, what can we say here? It does not mean that the body is not moving. It is moving, yes, but with now uniform speed. Therefore, I need to have drawn another curve here. Here we have velocity in meters per second. Here we have time. Suppose it is a straight line like this. How can we define the behavior of this body? It's a straight line. I know many students, some students can actually say that this body is actually stationary. It is not stationary. It therefore, because the gradient here is the dv, the change in velocity over change in time, is 0. But being 0 does not mean that the body is stationary. No, therefore it means that the body is not accelerating, but it's moving with uniform, constant velocity, maybe 20 meters per second. Those are the velocity time graph, and so much for the motion graph. Therefore, now we are going to look further into velocity time graph. We look what happens in the area of the curve. Suppose we have here, we say area under the velocity time graph. So suppose we have a curve here. This is velocity in meters per second, and here we have time in seconds. This is a body that started from rest, so it was moving. At time 0, it was not moving, so it's a straight line. And after some time t, it has, this is time, let me call it t. After time t, it acquires a velocity of v. The initial velocity is 0, the final is v. So this is the area under that velocity time graph. That started from 0, and after time t, it acquired a velocity of v. And therefore, what does this represent? Let's see. The area under the curve, how do we get the displacement? How do we get the distance traveled, or the distance? The distance is given by the speed, average velocity times time. Average velocity times time. So now we want to get the distance. Average velocity, what does that give us? Average velocity is given by what? The initial velocity, which from here is 0, plus the final velocity is v. Because I have said this body starts from 0, and after time t, it acquires a velocity of v. So what's the average of that? It's this one minus that to get the average of the whole journey. We divide by 2 because we are doing the average. It's like when you have a boy who gets, in one cut gets 40%, in the other cut he gets 60%. So what's the average of those two cuts? It's 40 plus 60 divided by 2, which is 50. So we have the initial velocity is 0, final is v. We do the average for that. And then we multiply that by the time taken. So we multiply that by time taken, which is t. So we see it is going to be a half v t. A half v times t, we can see from here, it is the area under this curve. So we're looking at this one here. Is this one correspond to the area of this curve? Because how can we get the area of this triangle here? Is area of a triangle is given by a half base times height is equals to a half base is, the length is t, times height is v, which is a half vt. So what am I driving at? I would show you that the area under the velocity time graph gives the distance traveled by that body. And I take it again that the area under the velocity time graph, it gives the distance traveled by that. We can look at one example. Suppose this one is now this is 2, and this is 20 meters per second, this is 10. And you have to calculate the distance traveled by this body in kilometers or in meters. Calculate the distance. So you say here the distance is equals to area under the graph. And how do we get the area of this triangle? It's a half. Base is 4 seconds times height, which is, the height here is correspond to this, which is 20. So mathematically, we need to work this out to by 2 and by 2. Let me multiply this one to 10 to have 40 meters. So that's the distance traveled by that body. For now, we are going to stop there. In our next lesson, we are going to proceed with more examples involving the area under the velocity time graph, and proceed with this topic. For any questions or any comments or any opinion, please do not hesitate to write to us, an SMS to us, which is 21126. Write the number SMS to 21126 for any questions, comment, or any opinion, or any physics figure tip. So thank you so much for tuning into our physics class. Let's meet next time. Bye-bye.